All right, so now we're ready to do our examples about L'Hopital's rule. Okay, so we're going to revisit these first examples. Are going to be straightforward L'Hopital's rule that we learned last year. Okay, so what do we know about a limit? The first thing you always try to do in a limit is do direct substitution, right? So this problem says we want the limit as x approaches 1. So the first thing we're going to do is we're going to plug in a 1 and see what happens. All right, so when I plug in a 1 here, the natural log of 1 gives me a 0 answer. I plug a 1 in the bottom, 1 minus 1 gives me a 0 answer. So this is giving me 0 over 0, which is an indeterminate form, which we learned last year. So when you have an indeterminate form, then you apply L'Hopital's rule. L'Hopital's rule is just where you take the derivative of the top function. So the derivative of ln of x is 1 over x. Then you take the derivative of the bottom function. So the derivative of x minus 1 is 1. And now we're going to go again. We are going to substitute in a second time. Just do regular substitution. So we're going to plug in a 1. So now when I plug in a 1, I get 1 over 1. So now I can put an equal sign. Never put an equal sign here. Don't say it equals 0 over 0. They will count that wrong on the AP exam. So that's why I did not do that. So here, when I put in a 1, I can actually put equals because I can actually get a number here. This is 1 over 1, so the answer is 1. Boom, we're done. Okay, that's the answer. We started out with an indeterminate form because when we plugged in 1 the first time, we got 0 in the numerator and you got 0 in the denominator. That's that indeterminate form, 0 over 0 or infinity over infinity. Then we can do L'Hopital's rule where you take the derivative of the top function, the derivative of the bottom function, and then substitute in again. Do straight up substitution. So these first problems are straight up L'Hopital's rule like we learned last year, just to review real quick. Okay, do the same thing. First thing you do is direct substitution. So put a 1 in here, that's going to be a 0 on the top. Put a 1 in the bottom, that's going to be 0 on the bottom. So I've got an indeterminate form. I'm going to use L'Hopital's rule. So the limit as x approaches 1. So I take the derivative of the top, which is 2x minus 1. Take the derivative of the bottom, which is just going to be 2x. Now try again. We're going to substitute in a 1. All right, when I plug in a 1 in the top, I get 1. When I plug in a 1 in the bottom, I get a 2. So I'm actually getting an answer of 1/2, and that is the correct answer. All right, this is L'Hopital's rule from last year. I haven't done anything new yet. All right, put in a 0. The sign of 0 is 0. Put in a 0 there, that's 0. So I'm getting an indeterminate form, 0 over 0. So I'm going to do L'Hopital's rule. Okay? The derivative of sine is cosine. The derivative of x is 1. So now I'm going to plug in 0 again. When you put in a 0, the cosine of 0 is 1. I've already got 1 in the denominator. So that answer is 1. Boom, we're done. Got that one. All right, so you're doing direct substitution. As long as you don't get 0 over 0 or infinity, just keep going. We're doing good. All right, find the limit. So we're doing the limit as x approaches infinity. Okay, so let's plug in infinity. So put an infinity in here. E to the infinity is infinity. And when you put infinity here, infinity squared is infinity. So I'm getting infinity over infinity. So that means I'm going to do L'Hopital's rule. So L'Hopital's rule is take the derivative of the top function. Well, the derivative of e to the x is e to the x. And then take the derivative of x squared, that's 2x. Try again. All right, so let's say it's put infinity in here. Well, e to the infinity is infinity. And then put infinity here. 2 times infinity is infinity. So I'm getting infinity over infinity again. So let's do L'Hopital's rule one more time. Let's see. The limit as x approaches infinity. So the derivative of e to the x is e to the x. And then the derivative of 2x is 2. So now I'm going to do direct substitution again. Put infinity in. E to the infinity is infinity. And then I just got a 2 on the bottom. All right. So infinity divided by 2. Infinity divided by 2 is infinity. All right, so I did get an answer for that one. This does give me infinity over 2, which is infinity. So that is the correct answer, infinity. All right, which is D and E, right? But if you can give me an actual answer of either positive or negative infinity, then you ought to do that. But it is the same as D and E, does not exist, but the actual answer is infinity. Alrighty, so what about this one? Change the color up a little bit. All right, I'm doing the limit as x goes to infinity, so let's put infinity in here. So what happens when we put infinity in here? The limit, the natural log of infinity. As x goes to infinity, what happens to the natural log? Well, that's infinity, okay? And then what about putting infinity in the bottom? So the cube root of infinity is also infinity. Now remember ln of x, what that equation looks like here. Natural log of x looks like this. It's just this curve right here. So as x goes to infinity, y is getting larger and larger and larger. So that's why that's infinity, if you're still thinking about that one. And then the cube root of infinity is going to be infinity. So I'm getting infinity over infinity, which is indeterminate form. So I'm going to do L'Hopital's rule. And I'm going to take the derivative. So the derivative of ln of x is 1 over x. And then down here on the bottom, the derivative of x to the 1/3 is going to be 1/3 x to the negative 2/3. All right. So let's do some math on this, so we can figure this out here. Let me write it out, because I'm not going to put anything in it at the form that it's in. This is 1 over x, and then this is really 1 over 3 x to the 2/3. So I took the derivative, 1 over x, and then the derivative, this is x to the 1/3. Cube root of x is the same as x to the 1/3. So when I took its derivative, that was 1/3 x to the negative 2/3. And negative exponent needs to be in the denominator, so that's 1 over 3x to the 2/3. Now, the reason I wrote it that way is so I can do outers over inners. Okay? So this is going to give me the limit as x approaches infinity of outers, 3x to the 2/3 over x. The inners are x times 1. And this can simplify. I'm just doing algebraic stuff. And so what do you do when you have a quotient? You subtract your powers, right? So this is x to the 2/3 minus, and then x to the first. So it's 2/3 minus 1. So it's x to the negative 1/3. So this ends up being x to the 1/3 in the denominator, because there's 2/3 up here, 1 whole down here. So if I cancel x to the 2/3 out, then I'm left with an x to the 1/3 in the denominator. I guess is a good way of saying that. But you're just subtracting. When you divide powers, you subtract your exponents. 2/3 minus 1 is negative 1/3. So that means I have an x to the 1/3 in the denominator. All right, so now all I did was just do an algebra. So now let's do plugging in. Okay, so when I plug in, then I've got infinity on the bottom. So this is going to be 3 over infinity, which that equals 0. Okay, because you're dividing 3 by a really big number, so that's going to go to 0. So all I did on this, when I first put infinity in, I got infinity over infinity, so I did L'Hopital's rule. I took the derivative of both of them. But the difference with this problem was I had x's on the top and the bottom, so I just did some algebra to simplify. All right, and then once I got it simplified, then I went on and plugged infinity in again, and I have a whole number, an integer in the numerator, and the bottom ends up being the cube root of infinity, which is still infinity. So 3 divided by infinity gives me 0. All right, so there's a whole bunch of, I was just doing ones a little bit harder, dealing with L'Hopital's rule. Okay, so the first thing you're going to do here is you're going to put in a 0. So if I plug in a 0, the tangent of 0, what is the tangent of 0? The tangent of 0, think about that on the unit circle. If you're here at 0, that's the point 1, 0. So tangent is sine over cosine, so that's going to be 0. And then here it's 0, so 0 minus 0 is 0. And then, of course, putting a 0 down here, 0 cubed is 0. So I'm getting an indeterminate form, 0 is 0. So what do? You take the derivative. Do L'Hopital's rule. You don't do quotient rule. You're doing the derivative of the top and the derivative of the bottom. All right, so the derivative of the top, the derivative of tangent is secant squared. And then minus the derivative of x is 1. And then the derivative of x cubed is 3x squared. So there we go. All right, so that one now, we want to know what happens now when we take the limit as x goes to 0 for this. Now, I gave you a little hint up here. The limit as x goes to 0 of secant squared is 1. So if you plug a 0 in here, you're going to get 1 minus 1, that's 0. And then plug in a 0 down here, you're going to get 0. So we're getting 0 over 0 again, so I got to take the derivative a second time. Well, not the derivative, not doing Hody-High, but doing L'Hopital's rule. So we got to do L'Hopital's rule again. All right. So I need the derivative of secant squared. So if you think about this, that is secant x quantity squared. So I got to take its derivative. So I got to do power rule first. So that's going to be 2 to the front, then drop a degree. So then that'll be secant x to the first. And then I need to chain on the derivative of the inside. So the derivative of secant is going to be secant tangent. So I'm doing the derivative because I'm doing L'Hopital's rule again because I got 0 over 0. So the derivative of secant squared, I rewrote it with a 2 on the outside. So then I did power rule, 2 to the front, drop the degree, and then chain on the derivative of the inside, which is secant tangent. Then the derivative of 3x squared is 6x. All right. So now that gives us, if we simplify that a little bit, that's going to give us 2 secant squared x tangent x over 6x. That's what you get when you simplify that. So when you plug in 0, well, we already know the tangent of 0 is 0, and then we're putting a 6. So I'm getting 0 over 0 again. Oh my goodness gracious, when is this ever going to quit? Right? So I'm getting an indeterminate form again. So I'm going to do L'Hopital's rule again. Now this time I have a product. Okay? So we have a product right here. So this will be my first function, and this will be my second function. So when you do product rule, you've got first function times the derivative of the second function, and the derivative of tangent is secant squared, plus second function times the derivative of the first function. So now I've got to do 2 times the derivative of secant squared. Well, we already did that up here. So the derivative of secant squared is this right here. So I'm just going to put a 2. So that's going to be 4 times secant squared x tangent x. I'm just going to use that because I already know the derivative of secant squared is this right here because I just did it right there on that line. All right. And so I've got 2 secant squared, so I just doubled this. I just made it 4 secant squared tangent squared. Are you with me? All right. So now on the bottom, I got to take the derivative of 6x, and so that gives me 6. All righty. So now let's see what happens. I'm not going to get 0 on the bottom anymore, right? Because the derivative of 6x is 6. So I'm not going to get 0 over 0 any longer. So this should be the end of the deal. Okay. So when we put in 0, we already know the tangent of 0 because we've done it multiple times up here, right? When you plug in 0, tangent of 0 was 0. Come on, pen. All right. So I already know that this part right here, when I plug in a 0 for these tangents right here, that is 0. So this part's going to equal 0. So all I need to do is figure out this part right here. So I've got secant squared. So I need to think about what is the value of secant. Okay. Now secant is the reciprocal of cosine. Right? So if I'm doing the secant of 0, that's really the reciprocal of cosine at 0. Well, what's the value of cosine at 0? That's 1. So secant is going to be the reciprocal of 1. So secant is 1. So secant's 1. You're going to square those. So this is really 2 times 1 squared times 1 squared. So that's going to give me 2 over 6. So the answer is 1/3. Whew, that was interesting. All right. Now this one, I warned you, this is watch out, find the limit. This is the last one. So I want to just plug in pi and see what happens. Okay, so plugging in pi. So what is the sign of pi? The sign of pi, if you think about it on the unit circle, if you're at pi on the unit circle, you're over here, and you're at the point -1, 0. So what is the sign of pi? Whoops, let's not put an equal sign until we know for sure. All right, the sign of pi is 0 because it's the y-coordinate. Then we've got 1 minus the cosine of pi. What's the cosine of pi? -1. So look at what we're getting. We're getting 0 divided by 1 minus -1, which is going to give us 0 over 2, which is actually 0. I'm not getting 0 over 0 because the cosine of pi was -1, and so that becomes addition, so you don't get 0 on the bottom. So you end up with 0 over 2, which you can calculate. 0 divided by 2 is 0. So you got to watch out sometimes. You think you're automatically going to get 0 over 0 and then use L'Hopital's rule, but sometimes you don't. So I just like to warn people of that sometimes. All right, now let's get into the new things. So this says find the limit. So we're doing the limit as x approaches 0 from the right. All right, so we're coming towards 0 from the right, and the reason I'm doing that is because ln of x looks like this. So if you want the limit as you approach 0 coming from the right, that's going to -infinity, okay? So if I plug in a 0 here, that's 0. If I plug in 0 coming from the right for this, I'm getting -infinity. So what do I get for this? I get 0 times negative infinity. So 0 times -infinity is a product. So we need to, all right, so when you substitute in 0 for these, you end up with 0, and then putting a 0 in coming from the right for ln, coming from the right towards the origin, you're going to -infinity. So this ends up being, with direct substitution, you end up getting 0 times -infinity, which is an indeterminate product, okay? So what did they tell us to do when we had an indeterminate product? They told us to rewrite it as a quotient. So you want to write one of your expressions as a reciprocal. So you want to divide by reciprocal. So what I want to do here is I'm giving you a hint here what to do. We want to rewrite x as 1 divided by 1 over x. That's still x, okay? So 1 divided by 1 over x is actually x. So we want to divide, so we're rewriting this limit as a quotient. So I'm going to do the natural log of x divided by 1 over x. So I'm going to take the natural log of x and divide by the reciprocal of x. And that'll give us a new form. All right, so now let's plug in 0. What do we get? If I plug in 0 from the right for ln, coming from, again, from the right side, that goes to -infinity. So this is -infinity. And then putting 0 in here, 1 divided by 0, that's infinity. So what I've done is I've made an indeterminate product. I've made it now an indeterminate quotient, which is L'Hopital's rule that we're used to. We know what to do when we get infinity over infinity. So now that I've transformed it from being a product that you can't calculate by rewriting it, I now have infinity over actually -infinity over infinity. I'm allowed to use L'Hopital's rule. So to do L'Hopital's rule, all I have to do is take the derivative of the numerator and the derivative of the denominator. So what is the derivative of ln of x? Well, that's 1 over x. And then what's the derivative of 1 over x, right? 1 over x is the same as 1x to the -1. So his derivative is -1 x to the -2, which is -1 over x squared. So his derivative is -1 over x squared. So now you just got to do your algebra. So the easiest thing to do is to do outers over inners, just like I did on the other problem a few minutes ago. So now we just got to simplify this because we add the x's in the top and the bottom. So we're going to simplify. So we're going to do outers. So 1 times x squared is x squared over inners. X times -1 is -x. And now we're just going to simplify this. The limit as x goes to 0 from the right. So we got x squared divided by negative x, so that's going to leave us with negative x. Okay? So now what happens when you plug a 0 in there? You get 0. All of that for the answer 0. Okay? Let's look at this one. This one says find the limit. So we want the limit as x approaches pi over 2 from the left. Well, the secant, as you approach pi over 2 from the left, that's going to give you an answer of infinity. Because if you know what the graph of secant looked like, okay? Secant is a reciprocal cosine, all right? So cosine looks like this, all right? Secant is where you take it and you flip these guys out like this. So secant is where you flip them out. So we're doing pi over 2, which is right here. So if I approach pi over 2 from the left, so I'm approaching pi over 2 from the left, that's going to infinity right here. So that's going to give me infinity minus. Now what does tangent look like? All right, tangent looks like this, where this is negative pi over 2 and this is positive pi over 2. So tangent looks like this. So what are we doing as we approach pi over 2 from the left? He's also going to infinity. So this is actually giving us infinity minus infinity. Oh no, we got a problem. So that's a difference, all right? An indeterminate difference. So how did they tell us to do? They told us different things to do for a difference. There's different things. Well, one thing you can do is use a common denominator. So think about what these two guys are. All right, these two guys are actually, if you think about what they are as fractions, the secant is 1 over cosine, and tangent is sine over cosine. So now if I put that together as a common denominator, I'll have 1 minus sine over the common denominator of cosine. Okay? So now, what happens when you put pi over 2 in here? So at pi over 2, guess what? The sign is 1 at pi over 2. So think about it on the unit circle, where you are on the unit circle when you're at pi over 2. You're up here. So you're at 0, 1. So the sine of pi over 2 is 1. So this is going to give me 1 minus 1, which is 0. And then at pi over 2, the cosine is the first coordinate, so that's giving me 0. So what I've done is I've transformed this difference that you can't calculate, indeterminate difference. By rewriting it, I now have made it 0 over 0, which is normal L'Hopital's rule. So now I can just do normally what we normally do with L'Hopital's rule. All right? I can just take the derivatives. So the derivative of 1 minus sine, well, the derivative of 1 is 0, and the derivative of sine is cosine, so that's going to be negative cosine. And the derivative of cosine is negative sine, so the negatives are going to cancel. All right, so we're just going to have cosine over sine. So now we can just plug in pi over 2. So what is the cosine of pi over 2? 0. What is the sine of pi over 2? 1. So what is 0 over 1? 0. All of that worked for the answer 0. But what we did was we took a indeterminate difference and we rewrote it using common denominators. And when you did that, it gave you, when you did direct substitution, that gave you an indeterminate quotient, the 0 over 0 that we're used to from last year. So then you just take your derivatives, which is L'Hopital's rule, plug in again, and you're able to get the answer. Right? So basically, these are all just change the forms so that you can get what you need. Okay? Now this one, number 10. Find the limit. So what's going on in this one is we have the limit as x approaches 0 from the right of 1 plus sine 4x raised to the cotangent x. All right, so if you do this, if you put a 0 in here, the sine of 0 we know is 0, so this is going to be 1. But the cotangent of 0 is undefined, that's infinity. So we're actually getting 1 to infinity. So this is one of the power problems. All right, this is a power problem. So what you do is you rewrite the problem and take natural log. Okay, so we're going to rewrite the problem. So I'm going to do y equals 1 plus sine 4x raised to the cotangent. And I'm going to do logarithmic differentiation. Okay, so logarithmic differentiation is what we did last year, where you just take the natural log on both sides. And then the reason you do that is because now you can use a law of logarithms, and you can move this exponent to the front. Okay, so now you've moved your exponent to the front. Okay, so now I've got this expression, ln of y equals the cotangent of the ln of 1 plus sine 4x. Now take the limit of that. Well, when you do the limit of this now, we're doing the limit as x goes to 0 from the right side of the cotangent x ln of 1 plus, because I'm just doing this new problem that I just did, but I'm really finding this. I'm doing the limit. Let's just keep note of this. We're doing the limit right now of ln of y, which is now this expression. So now I'm doing the limit as x goes to 0 from the right of this new expression that we just created. Okay? Well, this new expression that we just created, this is now 0 times infinity. So remember, we did have 0 raised to infinity. No, 1, sorry. We had 1 raised to the infinity. So now we have cotangent times this, which that's given me, oh, yeah, because it's ln of 1 plus sine. So now we have infinity times 0, because this expression here was the 1, and this is ln of 1, which is 0. So now we have the indeterminate product that is infinity times 0, which you can't do. So how do you fix that? You have to rewrite it as a quotient. So what we've done is we had an exponent where we had 1 to infinity. Okay, so we had to do logarithmic differentiation to fix that. Now that didn't help much, because now that we've got this nice little product and the ln is in there, at first it looks like we have 1 times infinity, because this was the same expression, cotangent, and this is the same expression, but we don't have 1 times infinity. We have infinity times the ln of 1, and the ln of 1 is 0. So now we've got the indeterminate product. So now to do the indeterminate product, we have to fix it by doing something that's going to put it into a fraction. Now I can easily put this into a fraction by rewriting cotangent. Okay, this is just multi-step problems. All right, so I'm going to rewrite the cotangent as 1 over tangent. All right, cotangent is the same as 1 over tangent. Okay, right? That's one of your reciprocal identities. Cotangent is equivalent to 1 over tan. Now, doing that, I've now written this indeterminate product as a quotient. Now, when you put a 0 in here, we end up with 0 over 0. So now we have 0 over 0, which is what we want, because now we can do L'Hopital's rule like we're used to. Let's change the color, change this up. So now I'm going to take the derivatives. So this is basically just manipulating the situation so that it works. All right, so we can get 0 over 0 or infinity over infinity. So now I'm going to take the derivative. So how do you take the derivative of your ln stuff? So remember, taking the derivative of ln, it is going to be a fraction. It's going to be the derivative of this expression over that expression, right? So what's the derivative of 1? That's 0. So then we've got the derivative of sine of 4x. The derivative of sine of 4x is going to be cosine 4x, and then you chain on a 4. So I'm just doing the derivative. So now on the bottom, do the derivative of tangent. Well, that's going to be secant squared. Okay? So now let's see if we can do direct substitution and see what happens. Okay? So let's put a 0 in here. So putting a 0 in for cosine. Cosine of 0, well, that's 1. So 4 times 1, that's going to give me a 4. And then down here, putting 0 in for sine. The sine of 0 is 0. So 1 plus 0 is 0. Is 1, excuse me. 1 plus 0 is 1. All right, because 1 plus 0 is not 0. All right, 1 plus 0 is 1. And then in the denominator down here, putting in a 0, remember secant is the reciprocal of cosine, and I already know cosine of 0 is 1, so the reciprocal of that would be 1, and 1 squared is 1. So this is giving me an answer of 4. Woohoo, yay! All right, now the thing is, I'm not done because I need to fix this. All right, because what we just found is we found the limit of the ln of y. Okay, so now I've got to figure out what actually is my answer. Okay, so y actually equals e to the ln of y. What we just found is we found the limit of the ln of y, and that equaled 4. So now to get the actual answer to the problem, which we said this was y is this expression. So actually to get the answer for y, we have to do e raised to the ln of y. This is the limit of ln of y. So this is our answer for ln of y. Okay? So the answer to the problem then, y is equal to e to the 4. So our answer to the problem is e to the 4. I know. But you have to remember what we did was logarithmic differentiation. We took the natural log of this problem. So we no longer was just finding the limit of y, we were finding the limit of the ln of y. So this answer over here is the limit for the ln of y. I don't want that. I want the limit of this problem, which is actually y. So the way to fix it is you raise it to the e so that those cancel, right? So e raised to the ln of y, those cancel, and you get y equals y. So I'm just substituting my answer I get here, e to that expression, and that's my answer. So the actual answer to this problem is e to the 4. That's the actual answer to the problem. And I know you're probably done with me already. That's okay. We're going to spend plenty of time working on this. It's why I'm doing it now instead of waiting 2 more weeks. I did not want to wait and do this 2 weeks from now. All right. So let's do one more just like this. It's the last one. Okay. We'll do one more just like this. So we want the limit as x approaches 0 of x to the x. Okay. Well, we already know that if we plug a 0 in here, you're going to get 0 to the 0. That is an indeterminate power. Can't do that. So how do you fix indeterminate powers? You use logarithmic differentiation. So what I'm going to do is I'm going to do y equals x to the x. So I'm calling this y, an expression of y. So y, my function, is x to the x. I'm going to do natural log on both sides. And the reason you do that is so you can pull the power out of the exponent, right? Pull that x out of there. So x moves to the front. All right, now I'm actually going to find the limit of this now. So I'm going to find the limit as x approaches 0 from the right of x ln of x, okay? Now that's actually finding the limit as x approaches 0 from the right of ln of y, which is not what I want. I actually want the limit of y. This is what I called y. So we're actually right now finding the limit of ln of y, which we have to go back and fix at the end when we're done, okay? So now think about what we got here. If we put a 0 in here, this is going to be 0, and then the ln of 0, think about what's happening. This is what the function ln of x looks like. If you approach 0 from the right, that's going down to negative infinity. So this answer for this problem is 0 times negative infinity, which is an indeterminate product. So what do we do when we have an indeterminate product? we have to make it a fraction, all right? You need to make it a quotient because you got to fix it. We can't have a product. So we rewrite this, all right? The best way to rewrite this is to rewrite the x divide by its reciprocal, all right? That's the easiest thing to do. So now when you do that, you try it again, plug in a 0. So when you plug a 0 in here, we know the limit as we approach x from the right goes to negative infinity. And then down here, plugging a 0 into this expression, 1 divided by 0 is infinity. So we're getting negative infinity over infinity. Well, the good news about that, that's our indeterminate quotient, which we can use L'Hopital's rule for that. Whenever you get infinity over infinity, you can use L'Hopital's rule. So L'Hopital's rule is just take your derivatives now, right? So this is just multi-stepped is what makes this complicated. Each individual step is not hard. It's just multi-stepped. So what's the derivative of ln of x? Well, that's 1 over x. What's the derivative of 1 over x? That's negative 1 over x squared. We did that a few minutes ago where I did 1x to the negative 1, and then we did the derivative, negative 1x to the negative 2, which is the same as negative 1 over x squared. So that's the derivative of that. Now, because we have x's in the top and the bottom, it would be better if we simplified it. So you do outers over inners. So that's going to be x squared over negative x. And then you can cancel. So that becomes x squared over negative x becomes negative x. All right. So now if I plug in a 0, I get the answer 0. Now remember though, that's not our final answer. That's the answer to this problem, the limit of the natural log of y. So to fix it, I have to do this. Y is actually e raised to my answer of ln of y. So y equals e raised to my answer, which is 0, and e raised to the 0 is 1. So the answer to this problem is 1. That's the answer to this problem. Because when I do all of this work and do the limit, I end up getting a 0 answer. But that's the answer for the ln of y. So to fix it, I have to make that the exponent on e. So we have e to the 0, which anything raised to the 0 power besides the indeterminate ones, that is equals 1. So that's my answer for that problem. So these are just algebra manipulations. So if you have, we normally do quotients. So if we get infinity over infinity or 0 over 0, we're good with L'Hopital's rule. If you end up getting a product, you got to fix it and make it a quotient. If you get a difference, you got to fix that and make that a quotient. If you have a power problem, you have to fix that using logarithmic differentiation. That will always usually make a product, and then you fix the product by making it a quotient. So it's just algebra manipulation. To be able to do L'Hopital's rule, you have to have 0 over 0 or infinity over infinity. So it's just algebra manipulation to get that to happen. All right, and so I'm giving you this early so that we can get lots of practice before our last week of school when we're doing problems that involve this.